All right, well, hello everyone, and welcome back. In this video, we will continue our review of second-order circuits, and we'll cover some additional examples illustrating our step-by-step recipe. So if you have not already done so, make sure you have first reviewed our previous video, which introduces second-order circuits. Let's go ahead and get started. So goals for today. Our goal is to continue practicing writing and solving second-order differential equations. And as we learned, in order to solve RLC circuits, we need to be able to solve a second-order differential equation. And once again, we will continue practicing our shortcuts and our 10-step recipe to make solving differential equations a little bit easier. So real quick, let's just briefly review what we covered in our previous video. You'll remember we learned that RLC circuits are circuits which contain one or more resistors, but also a single inductor and a single capacitor. We call these second-order circuits because the behavior is represented by a second-order ordinary differential equation. Here we've written the general form of this equation, and you can see that x of t is our current or voltage. And we see that the current or voltage behavior is represented by a second-order ordinary differential equation, and f of t is our input applied to that circuit. And as we mentioned in our previous video, the order of the differential equation is exactly equal to the number of capacitors and/or inductors in the fully simplified circuit. So we saw in our previous videos that a first-order circuit has just one inductor or capacitor, and here a second-order circuit has two inductors, two capacitors, or one of each. And that gives us the second-order differential equation. And last time we also learned that these RLC circuits and second-order circuits will have three general types of behavior. So depending on the circuit that we are given, it could behave in one of three possible ways. First, we have overdamped behavior. And we saw in overdamped behavior, we exponentially return to equilibrium, and there are no oscillations. Critically damped is typically our most desired case. And in critically damped behavior, we see that our circuit returns to equilibrium as quickly as possible. And then finally, we have the underdamped case. And in the underdamped case, we see that our circuit will have this oscillating pattern in its signal over time, and then the amplitude of these oscillations gradually decreases to zero. And so, how do we predict this behavior? You'll remember in our previous video, we can predict the behavior based on the relative value of our damping coefficient alpha and our resonant frequency omega naught. And you'll remember that alpha and omega naught can be taken directly from our second-order differential equation. The term in front of the first derivative gives us 2 alpha, and the term in front of the x of t gives us omega naught squared. So if we look at our differential equation, we can immediately predict which type of behavior our circuit will have. So again, I don't expect you to know how to derive these behaviors for the overdamped, critically damped, and underdamped case, but I do expect that you know how to determine alpha and omega naught, and I expect that you would be able to determine which type of behavior we have based on looking at the differential equation of a given circuit. And finally, last video, we introduced a recipe for solving second-order RLC circuits. And so what we'll do in this video is we'll go through a few more examples of using this recipe to solve actual problems. So, as much as possible, please make sure you go through the examples that we cover on your own and verify that you understand how to follow each step of this recipe. This recipe may seem like a lot of steps and a lot of work, but if you follow it, it will help guide you to the correct solution for your second-order differential equation. So with that said, let's go ahead and jump into some more examples for today's video. And I highly encourage you to follow along as we go through each of these examples. Finally, one last point to note is, of course, in our recipe, part of our recipe requires us to guess the form of our forced response. And so remember, when we need to guess our forced response in step 7, we can use the same guesses that we did in our first-order circuit cases. So let's now transition into doing some practice problems to better understand second-order circuits and to practice using that recipe. Let's start with a review question of the day. This question was actually part of an exam question. So suppose we know that the below circuit's current must be given by this second-order differential equation. So we are given a second-order differential equation for our current I of t in the circuit below. Notice that this second-order differential equation is written in terms of our inductance L, resistance R design, and our capacitance C. We are told the inductor is 7 henries. Capacitor has a capacitance of 2 microfarads. So capacitor is 2 times 10 to the negative 6 farads. But we don't know R design. We are told that we need to determine the required resistance for R design so that the circuit will have critically damped behavior. So let's go ahead and give this question a try. We want to determine R design so that the circuit will have critically damped behavior. Okay, so let's remind ourselves, how do we know whether we are critically damped? Let's just briefly remind ourselves of the rules. Notice that in order to be critically damped, our damping coefficient alpha must equal our resonant frequency omega naught. And remember, we can determine alpha and omega naught directly from our second-order differential equation. So we can use these bits of knowledge to help us in order to find our design. So remember, to be critically damped, we know that alpha must equal omega naught. And so from our equation, we can determine alpha and omega naught. So let's take a look. Remember, the term in front of the first derivative is equal to 2 alpha. So we can say that 2 alpha must be equal to our design divided by L. Similarly, the term in front of the I of t, that is omega naught squared. Omega naught squared must therefore equal 1 over LC. So in this case, we can determine that alpha must equal our design divided by 2L. Just move that 2 to the right-hand side. And omega naught must be equal to the square root of 1 over LC. Let's go ahead and substitute the other values that we know. We know that L is equal to 7 henries, and C is equal to 2 times 10 to the minus 6 farads. So if we substitute that in, we can determine that to be critically damped, alpha must equal omega naught. That means our design divided by 2 times 7 henries, that must equal square root of 1 divided by 7 henries times 2 times 10 to the minus 6 farads. All we need to do here is solve for our design. So we just need to do a little bit of algebra here, and we can determine that our design is simply equal to 14 divided by a square root of 7 henries times 2 times 10 to the minus 6 farads. And if we plug that into our calculator, we determine that the result will be about 3741.65 ohms. What that means is that if we want I of t to be critically damped in our first order circuit, our resistor R would need to have about 3741 ohms. So this is a very common situation that comes up in some of our assignments and labs, is figuring out what value do I need for a component in my circuit so that I get critically damped behavior. All right, and just for fun, I would encourage you, if you would like additional practice, Try solving this differential equation for I of t. And I'm not going to show the full solution here, but if you follow our recipe, you should end up with the following. If you follow our recipe, you should end up with I of t is equal to e to the minus 267.261t times negative 2138.09t minus 8 plus 8 amperes. So please consider to try solving this equation the rest of the way and verify that you get the same result. Let's now move on to our next example. All right, let's now try example 1. In this example, we are asked to find the differential equation and complete solution for the inductor current IL of t in the circuit below. We're also given some information about each component. We're told the inductor has an inductance of 10 henries, resistor has a 20 ohm resistance, and our capacitance is 0.001 farads. We are also told our current source is equal to U of t amperes. Remember, U of t is the unit step function. So recall from our previous video, U of t is equal to 1 for time t greater than 0, and equal to 0 for time t less than 0. Here we want to find our complete solution for time t is greater than 0. So generally, in an exam question or homework question, this should be very clearly stated. So in this case, since we have U of t amperes, we can assume that this is a 1 ampere current source for time t is greater than 0. Notice we are also given some initial conditions. So we're told initially our source is 0 amps at time t equals 0. And we're also told the time derivative of our current is also 0. Let's go ahead and give this example a try. And let's follow our 10-step recipe. So please consider following along with each step of our recipe as we complete this example. All right, let's start with our first step. The first step of our recipe is to verify that we have an RLC circuit. And in this case, we see that we've got one capacitor, one inductor, and one or more resistors. So, yes, we do have an RLC circuit. Second step is to determine our initial conditions. And here they are given in our question. If they were not given, then you would want to apply the steady state conditions and solve for those initial conditions. So in this case, they're already given to us, so we can say that we have I of 0 equals 0 amperes. And in this case, it's IL of 0. And DIL of 0 dt equals 0. So if those were not given, we would have just needed to consider our circuit at steady state for time t is less than 0, and we could have solved and likely come up with the same thing. Next is step 3. Step 3 is one of the most important steps. Here we need to find our differential equation. And specifically here, we want to relate IL of t, that's our inductor current, to our source, Is of t. And you'll remember that typically, to find the differential equation, we need to apply Kirchhoff's laws and often we need to use the toolbox equations for inductor and capacitor behavior. And so a big hint here is you really want to take a look at what kind of circuit you have. If your circuit has just one loop, Kirchhoff's voltage law might be a good approach. And here, if our circuit has a convenient node, you might want to try Kirchhoff's current law. So notice in this case, we have a very convenient node in this case. This top node is sitting at voltage Vc, or I could even write that my top node is sitting at voltage VL of t. And notice here VL of t actually equals our capacitor voltage for this particular circuit, because our inductor and capacitor are in parallel with each other. Well, wait a minute, that's a pretty convenient node, right? What tool in our toolbox is good for writing equations at a node of a circuit? In this case, let's apply Kirchhoff's current law to the top node of our circuit. We have this very convenient node, so it's pretty easy to come up with a Kirchhoff's current law equation. So I'm just going to go ahead and assign some currents. I've got I1 coming in, then I2, I3, and I4 leaving. And I know by Kirchhoff's current law that the algebraic sum of currents entering and leaving that top node must be 0. So now our goal is we need to rewrite this equation We need to rewrite that Kirchhoff's current law equation in terms of only our current source. Here, our current source is just u of t is 1 amp for time t is greater than 0. So we have our current source, and our equation should also be in terms of only IL of t. Because remember, our goal is to end up with that second-order differential equation, and it should be only relating our inductor current IL of t to our source current, which is just 1 ampere. So let's go ahead and see how we can take this Kirchhoff's current law expression and rewrite it so that it's in terms of only current source and inductor current. So we'll continue step 3 of our recipe. So here we have Kirchhoff's current law. So you'll remember, so far we have plus I1 minus I2 minus I3 minus I4 equals 0. We need to get each of these terms only in terms of inductor current or source current. So we need to substitute I1, I2, I3, and I4 with expressions. For I of t, in this case it would be for our current source, and our inductor current. Let's consider I1 first. The current I1 is exactly equal to our current source, so we can say I1 is simply equal to 1 ampere. Again, that comes from our u of t. How about our current I2? Our current I2 is the current through our resistor. And we know that our resistor has voltage VL of t on the top node, and we can say that our ground node is on the bottom. So I2 is the current through our resistor. And we can show that that current, I2, is just going to be equal to VL of t minus 0 divided by R, or just VL of t divided by R. Well, wait a minute. VL of t is not what we want. We want IL of t. How do we relate? How do we relate VL of t to IL of t? Is there another expression in our toolbox that we could use? How about this one? We know that our inductor voltage VL of t is equal to L times the derivative of our inductor current. So therefore, we can substitute in, and we can write that our current I2 can also be written as simply 1 over R times L dIL of t dt. So notice now we have our current I2 in terms of our inductor current IL. So we have completed I1 and I2. Let's now find an expression for I3. Well, I3 is the current entering our capacitor. And what else do we know? Well, we know for this capacitor, we know that the capacitor voltage Vc of t is equal to VL of t, and VL of t is equal to L dIL of t dt. So if we know the capacitor voltage, how can we get capacitor current? Well, let's remind ourselves. We know that the current entering our capacitor must be equal to our capacitance times the time derivative of our voltage. So using that, we can determine that our current I3 is simply equal to, in this case, our capacitance times the time derivative of our capacitor voltage, which is L dIL of t dt. So therefore, our current I3 is going to be equal to C times L times the second derivative of our inductor current. Finally, the last term in our Kirchhoff's current law expression is I4. And I4 is simply equal to IL of t. That's the current through our inductor. So notice, now that we have expressions for all of the currents, for I1, I2, I3, and I4, in terms of IL of t, we can substitute into Kirchhoff's current law and find our second order differential equation. So let's go ahead and substitute each of these currents, I1, I2, I3, and I4. Let's substitute these in and see what we get. So once again, our I1 term was just equal to 1 ampere. That was our U of t at time t is greater than 0. So I1 is 1 ampere. Then we subtract I2. I2 is equal to 1 over R times L dIL dt. Then we have I3. I3, we determined, was CL times the second derivative of IL of t dt. And then finally, our I4 term was just IL of t. Notice that we do have what looks like a second-order differential equation. We just need to rearrange and simplify to get the equation in the desired form. So let's go ahead and rearrange this thing. I'm going to write my terms in descending order, starting with the second derivative. And to get rid of those minus signs, I'm going to move my right three terms to the right-hand side of the equation. That way I get rid of the negative signs. So if I do that, I get LC t squared IL of t dt squared. Then I have plus L over R dIL of t dt. Then I have plus IL of t. And that is going to equal, on the right-hand side, I have my U of t, which is just 1 ampere for time t is greater than 0. Notice here I need to divide both sides by LC to get rid of the coefficient in front of my second derivative. And so if I do that, I end up with t squared IL of t dt squared plus L over R divided by LC. That will give us 1 over RC dIL of t dt plus 1 over LC times IL of t. And on the right-hand side, that will be 1 over LC. So now all that's left here is I need to substitute. We know that we have L is equal to 10 henries. We know our capacitance is 0.001 farads. And our resistance is 20 ohms. Make sure you use henries, farads, and ohms units here to avoid possible unit errors. And if I substitute those terms in, I will get the equation in my desired form. And we'll get something like this. 1 over RC becomes 50. And 1 over LC becomes 100. Again, the reason for that is because the capacitance is a small decimal. And on the right-hand side, we have 1 over 100. So this is our second-order differential equation in the desired form. So that is the end of step 3. All right, so the good news is we just finished the hardest part of this question. All that's left is to solve this equation. And determine. IL of t. So to do that, let's continue with the remaining steps of our recipe. Let's continue with step 4. In step 4 of our recipe, we need to find the values of alpha and omega naught. And to do this, we can look at our differential equation. So if we take a look at our differential equation, you'll remember the term in front of the first derivative, that gives us 2 alpha. And the term in front of just our coefficient IL of t, this coefficient gives us omega naught squared. So by looking at our differential equation that we just determined, we can determine in this case that 2 alpha equals 50 and omega naught squared is equal to 100. So therefore, just by solving for alpha and omega naught, we determine alpha must be 25, omega naught must be 10. Now we can continue to step 5. In step 5, we need to find the roots of our equation. And remember, the roots, these come from the process of determining the natural response. And these roots are S1 and S2. We know from our recipe that S1 is a square root of negative alpha plus square root of alpha squared minus omega naught squared. And we also know from our recipe S2 is negative alpha minus square root of alpha squared minus omega naught squared. So if we substitute, alpha is 25, omega naught is 10, we can determine S1 will be negative 25 plus 22.9128, which gives us S1 is about negative 2.087. And if we do the same for S2, we'll have negative 25 minus 22.9128. That gives us S2 will be negative 47.912. So those are our roots of our differential equation. And in step 6, we use S1, S2, alpha, and omega naught to determine our natural response. Let's look back at our recipe. So in our recipe, we see that if S1, S2 are real and distinct, meaning they're different, then we're overdamped. If S1 and S2 are real and equal, then we're critically damped. If S1, S2 are complex, then we are underdamped, and depending on which case we have, we can identify our natural response. Here we see that S1 and S2 are real. They're just some negative numbers, and they're different from each other. So here, we are in case 1. We are overdamped. So here, since our alpha is greater than omega naught, and S1, S2 are real and different, we are overdamped. And so from our recipe, we use the overdamped natural response. So our recipe tells us that our overdamped response, IL comma N of T, that natural response is going to be equal to K1 e to the S1t plus K2 e to the S1t, or I'm sorry, K2 e to the S2t. So we substitute in S1 and S2, and we determine our natural response will be K1 e to the minus 2.087t plus K2 e to the minus 47.912t. So notice those roots that we found earlier, S1 and S2, we need those to find our natural response. Okay, so we found our natural response. The next step in our recipe is to find our forced response. Remember, the natural response is the case when there are no sources in our circuit, but we also need to find the forced response. I'll call it IL f of t. And that's the part of our solution that captures the independent sources and time-dependent sources in our circuit. And looking back at our equation, we see that our forcing function f of t here, our forcing function is a constant. So in our case, because we have a step source or a constant created by that step source, we are going to guess that IL f of t is a constant because we have a step source. And so remember that guess comes from our table in the Smart Mathematicians, where our source and forcing function is a constant or step source, then our forced response is expected to be a constant. So now that we've made that guess, we need to plug our guess, IL f of t equals n, back in to our differential equation and solve for the constant n. So if we do that, let's see what we get. So our differential equation was second derivative of our constant, second derivative of our forced response, plus 50 times first derivative plus 100 times n, and all of that must equal 1 over 100. So notice what happens here. Second derivative of a constant is 0. First derivative of a constant is 0. So we're left with 100n equals 1 over 100. So therefore, in this case, we can determine that our forced response constant n must equal 1 times 10 to the minus 4, or 1/100th divided by 100. Therefore, our forced response ILF of t is equal to 1 times 10 to the minus 4. Now that we have found our natural response and forced response, we can complete step 8, which is to find the complete response. And here we just need to sum our natural response and forced response together. So here we determine our complete response, IL of t, is going to be equal to our natural response, so remember our natural response was k1e to the minus 2.087t plus k2 e to the minus 47.92t plus our forced response, which was 1 times 10 to the minus 4. So remember, here, kind of in our step 8 and 9, we need to use the initial conditions to determine our constants, k1 and k2. So let's remind ourselves what our initial conditions are. You'll remember we were told that IL at time 0 is 0, and dIL of 0 dt is also 0. So we can substitute our initial conditions into our equation in order to find k1 and k2. Let's go ahead and do that. So our first initial condition, we know IL of 0 equals 0. If we substitute that in, we can write k1 e to the minus 2.087 times 0 plus k2 e to the minus 47.912 times 0 plus 1 times 10 to the minus 4. All of that must equal 0. Remember, e to the 0 power is just 1. So we determine that k1 plus k2 plus 1 times 10 to the negative 4 must be 0. Let's call that equation 1. We got one equation, two unknowns. So let's use our second initial condition to get another equation. Our second initial condition says that our time derivative of IL with respect to time must also be 0. So here we need to take the derivative of our complete response. So derivative of an E expression, that's just going to be minus the constant. So we get something like this. Remember, here we're plugging in time 0. And remember, the derivative of our constant is just going to be 0. So if we simplify this expression, remember once again that e to the 0 power is just 1. We will determine that minus 2.087 k1 plus negative 47.912 k2, that must equal 0. Let's call that equation 2. We have two equations and two unknowns. So we can plug them into a solver, like Wolfram, MATLAB, whatever solver you like, and we can determine that k1 will be equal to about 1.04 times 10 to the negative 4, and k2 will be equal to 4.55 times 10 to the negative 6. Oops, and be careful there, there's actually a negative sign in front of the k1 term. So make sure you are careful to remember those negative signs. Once we've found k, then we are finally finished, because we can now write our complete solution with the values of k. And here we determine that IL of t is therefore equal to k1 e to the minus 2.087t. So that is minus 1.04 times 10 to the negative 4 e to the minus 2.087t. Then we have k2, so plus k2 is 4.55 times 10 to the minus 6 times e to the negative 47.912t. Finally, plus 1 times 10 to the minus 4. And units here are amperes. So finally, we have followed our complete recipe and determined the full solution for inductor current IL of t for time t is greater than 0. That was definitely a long question. And generally on exams, there's not enough time for me to ask you to do the entire full recipe from start to finish. So usually things like initial conditions may be given, or you would have a calculation that's a little bit shorter to complete. So please keep in mind that for the purposes of exams, the questions I would ask here would be short enough that you'd be able to finish within the exam time, but you do want to make sure that you fully understand how to complete each step of this recipe. So definitely take the time to go back and practice this example and verify that you're able to get the same result that I did. All right, let's go ahead and try one more example. By now, you're probably noticing that one of the most challenging parts of solving these questions is just finding that second-order differential equation. Once you've found the second-order differential equation, the solution is generally straightforward. It's just a matter of plugging in and simplifying. But sometimes it can be a little bit tricky to find that second-order differential equation. So in this example, example 2, we'll illustrate a few more strategies on how to determine that second-order differential equation. And please keep in mind that if I were to ask a second-order circuit question on exams, I would design the question to be finishable within the exam time. So let's take a look at this example. We are given this circuit, and we're told that the resistors are 1 ohm each. The inductor has an inductance of 0.5 henries, and the capacitance is 1/12 of a farad. We are also told that we have a sinusoidal source. Notice here, because we have that u of t in there, we can say that this Vs of t equals 5 cosine t times 0, or 0 for t less than 0, and it equals 5 cosine t times 1 for t is greater than 0. So that unit step function u of t is basically just helping us capture the time dependence of this source. And it's telling us that this 5 cosine t source is powered on at time t equals 0. So here, we want to write the second order differential equation for our capacitor voltage Vc of t for time t is greater than 0. So we want to see how our capacitor voltage will behave at time t is greater than 0. Notice that this question is just asking us to write the second order differential equation. So you're not required to solve it in this particular question, but you might see something similar on a future homework assignment. So let's go ahead and give this question a try. And in this case, we can follow the first few steps of our recipe. Now we definitely can verify that we have an RLC circuit. And then the second step of our recipe, if we were following it, would be to find initial conditions. In this case, we're just looking for the second order differential equation, so we don't need our initial conditions yet. But this is when we would find our initial conditions. So in this case, we actually don't need to determine this for this problem because we are just looking for our differential equation. But if you did need to determine those initial conditions, the best approach would be to draw the circuit at steady state. And we know for time t is less than 0, we would know that Vs of t is 0. Our inductor would behave like an open. Inductor behaves like a short, capacitor behaves like an open. And we could use the circuit at time t is less than 0 to find Vc at time 0 and dVc of 0 dt. Here we don't need these initial conditions, so we'll just move on to step 3 for this question. So in step 3, we need to write our second order differential equation. Which relates our Vc of t to our source, Vs of t. So once again, a good strategy is to apply Kirchhoff's voltage law or Kirchhoff's current law. Kirchhoff's voltage law is good if you have a single loop. And often Kirchhoff's current law is the best one to apply if you have a convenient node. So which one would we want to apply in this case? Well, if we look at the circuit we're given, there's a very nice node between our resistors. So in this particular question, given that we have a nice convenient node at the top of our circuit, let's apply Kirchhoff's current law to the node just above the inductor. If we assign a ground to the node directly below the inductor, we see that this top node has the top node has voltage VL of t, or the voltage at that point at the top of our circuit will be equal to the voltage across our inductor. So knowing that this top node is sitting at voltage VL of t, that's going to be helpful later. Let's go ahead and apply Kirchhoff's current law and look at how we can derive a useful differential equation. So in this case, I'm going to go ahead and label some currents. I'm going to assign I1 entering from left to right. I'm already given IL of t that's flowing downward. And I'm also going to label IC of t, that's my capacitor current that is exiting my node and entering my capacitor. I'm also going to assign a ground node below the inductor, and I'm going to recognize that the voltage at the top of my node above the inductor is VL of t. So by Kirchhoff's current law, I can write the equation that plus I1 minus IL of t minus, in this case, it will be IC of t. Those must all sum to 0. I'm going to call this equation 1. We need to rewrite this equation in terms of only our capacitor voltage Vc of t and our source Vs of t. So if I want my second order differential equation, I need to rewrite this equation so that I'm only in terms of capacitor voltage and source voltage. So we need to write some more equations here. Let's first consider our current I1. Well, by node analysis, we can recognize that I'm sitting at ground on the bottom of my circuit. So the point immediately to the left of my resistor, that point is sitting at Vs of t volts, or 5 cosine of t volts. Therefore, I can write that my current I1 is going to be equal to my voltage 5 cosine t minus VL of t, so the voltage on either side of my resistor, divided by my resistance, which is 1 ohm. I'm going to call this equation 2. All right, let's continue with the other currents, and then we'll see how to deal with this VL of t term. Because notice, we're going to need to get rid of VL of t and replace with a VC of t. So let's look at our next currents first. Next, let's consider IL of t. Well, that's just the current through my inductor. So I know from our toolbox, I know that IL of t is just going to be equal to 1 over L, that's my inductance, times the integral from 0 to t of my inductor voltage, VL of t. So once again, I have this VL of t term that I'm going to need to replace. But let's not worry about that just yet. So I found an expression for I1. I found an expression for IL. Now I need an expression for IC. Well, we know an expression that relates capacitor current to capacitor voltage. Remember from our toolbox, IC of t is just going to be our capacitance times dVc of t dt. So notice, I'll just call these equations 3 and 4. We now have equations that we can substitute in to Kirchhoff's current law. But before we can substitute, we need to replace the VL of t in equations 2 and 3 with an expression for Vc of t. Remember, we have to have our equation in terms of only Vc of t and Vs of t in order to get the second order differential equation that we want. So we need another equation relating VL of t, or our inductor voltage, to Vc of t. Well, to find that equation, let's consider our right-hand loop. So notice we can apply Kirchhoff's voltage law to this right-hand loop. And if we do that, look what we get. If I walk clockwise around my circuit, I can determine that plus VL of t minus, we have the resistance R times IC of t, minus Vc of t equals 0. So if I rearrange, I can determine that VL of t is going to be equal to RIC of t. In this case, our resistance is just 1 ohm, so that gives us IC of t plus our capacitor voltage Vc of t. And remember, IC of t, well, we know what that is. IC of t is also related to our capacitor voltage Vc. We know IC of t is C dVc dt. So we can determine that VL of t is also equal to C dVc dt plus Vc of t. I'm going to call this equation 5. And now that we know this equation 5, we can substitute equation 5 into equations 2 and 3. And then we can substitute everything into Kirchhoff's current law, that's equation 1, and that will give us our second order differential equation. So there's definitely a lot going on here, but you'll see that everything will come together very nicely. Let's go ahead and perform that substitution. So let's substitute our equations 2, 3, 4, and 5 into our Kirchhoff's current law equation. That was our equation 1. So here's what we get. First, we have our I1 term. I1 was just 5 cosine t minus VL of t over 1 ohm. Notice VL of t is given by equation 5. So we can substitute equation 5 into the VL for equation 2. And we end up with 5 cosine t minus Vc of t minus C dVc of t dt. So that's our first term. Then we have IL of t. IL of t is equation 3. So that is the 1 over L times the integral of VL of t. And, once again, VL of t, we know that expression down here in equation 5. So if we substitute that in, we have minus the integral of 1 over L times the integral from 0 to t of, here we plug in our expression for VL of t. So this integral is Vc of t plus C dVc of t dt. And then finally, we have to plug in our IC of t term. And remember, IC of t, that one nice and simple, that's just equation 4. IC of t will just end up being minus C dVc of t dt. And all that stuff must sum to 0. Notice we have an integral. Let's take the derivative of both sides. To get rid of the integral. And if we do that, 5 cosine t is going to become minus 5 sine t. Vc of t becomes minus dvc of t dt. Minus c dvc dt becomes minus c d squared vc of t dt squared. Integral goes away, so we multiply 1 over L through to both terms. So be careful of signs here as you multiply. We get minus 1 over L vc of t minus c over L dvc of t dt. And then finally, we have our time derivative of the last term, which gives us minus c d squared vc of t dt squared. And all of that sums to 0. You can see we're getting closer and closer to that second-order differential equation. Let's now combine like terms. And if we do that, we can also move the minus 5 sine t to the right-hand side. If I do this, let's see what we get. So I'll take my highest order terms first. Notice I have a minus 2c d squared vc of t dt squared. That's my two second derivative terms together. Then next, I have a negative 1 minus c over L. I'm just going to leave it written like this. This is a dvc dt term. So notice I'm just combining my dvc dt and my minus c over L dvc dt. And then finally, I have my minus 1 over L vc of t. And all that must equal 5 sine t. We are very, very close here, everyone. Notice I just need to divide both sides by 2t. I'm sorry, divide both sides by minus 2c. And we will have our equation in the desired form. So be careful here. Notice we're dividing by negative 2c. So if we do this, we end up getting d squared vc of t dt squared. Then that whole quantity gets divided, so we have minus 1 over 2c times negative 1 minus c over L. And then we have plus, again, watch the signs here, 1 over 2cl vc of t. And all of that will equal negative 5 divided by 2c times sine t. Our last step is to substitute. We know that our inductance L is 0.5 henries. C is 1 over 12 farads. So if we substitute those values in, we will get the final result, d squared vc of t dt squared plus 7 dvc dt plus 12 vc of t equals negative 30 sine t. So this leaves us with the second-order differential equation that represents our second-order circuit. And in a future homework assignment, you might be taking this the rest of the way through the recipe in order to solve for VC of t. All right, so thanks everyone for joining the fun in today's video. Hopefully now you're starting to get more comfortable with these second-order differential equations. You should now be able to follow our step-by-step recipe to write and solve differential equations for second-order circuits. So definitely make sure that you keep these equations and tools handy to help simplify the differential equations and make life easier. Also, please make sure you go back through these examples on your own. The first few times you try these kinds of problems, it's going to be intimidating. It's going to be weird. It's going to be uncomfortable. But they become much easier after you practice a few of them on your own. So please take the time you need to go back through these examples and practice them on your own. And take advantage of our assignments and additional examples to help you get comfortable with the recipe. In our next video, we're going to learn some additional tools that will help us avoid solving these second-order equations altogether. We'll see how phasors can help us greatly simplify any circuit containing an AC source. Thanks everyone, and we'll see you in the next video.